Not?
I wouldn't know.
Oh wait, I thought you watch them all and you like them.
I only watch the ones I miss. You
Oh,
know
okay.
this. And I like the ones so you know that I watch them. That's really what that is.
It's all that matters.
The problem is I use that as like an excuse to skip
Oh,
class
you
and I
got
never
you
watch
one.
them.
Yeah, I
He
do.
records
It's
the
like, oh, he
lectures, I
records the
cannot go
lectures.
there, I just never watch.
And you never watch them?
Yeah.
I would never do that, so you don't.
No, I
No, and I know that's what I appreciate about you. Let's take a minute to just bring ourselves into this room, especially after all the shenanigans and tariff talk. All right. Oh, perfect. Worked out perfect. All right, just settling in. Can you get here all at once and stay here for the bell's duration? Lovely. Kind of magical. The way the world just kind of comes back in, starts mixing in, and very beautiful.
Did you get the 20?
Yes.
I also like the way the bell, you can start to hear the major overtones toward the end. You know that like whoa, whoa, the big envelope comes in. So the higher frequencies die out. That's cool. All right. So yes, so these, I would like to collect these on Monday. Normally you would just have like a class period to do these, but you've got lots and lots of class periods theoretically.
Sunday from 10 p.m. to midnight.
Yes, start a Sunday night,
Just gotta do it eventually.
10 p.m.
As long as it's before class.
As long as it's before class. Yeah, you do you. I mean, I'm not gonna like
I mean,
cramp
honestly,
your
Monday
stuff.
at 11 a.m. doesn't sound too bad either.
I mean, that's pretty good. Get it done early so you do whatever you want later in the day.
Right.
That's
right.
cool.
Right.
Yeah, that's good. It's always good to wait till the last minute. That's good stuff. That's just good. That's good strategy. So with these, I would like them to be written up nicely so that you have, because you do have time. So maybe do some scratch work on other paper and provide me your final beautiful answer. I would like things, yeah, as narrated as possible,
No
please.
violent erase marks.
Write it in calligraphy.
What's that?
No violent erase marks.
No violent erase marks. What is that, Daniel?
It's in calligraphy. I do have a couple calligraphy pens I could write in there.
That'd be.
It's cool. So yeah, you can do that between 11 and 2 on Monday.
Yeah.
You could
I
record.
feel like Wheeler himself did it.
Yeah. When he was 5, like little baby Euler doing this stuff. All right. If you end up like screwing it up and you're like, oh, I screwed this up and I'm gonna have to do some major scratch outs, I'll just send you a new one. Just let me know and I'll send you a freshie. It's easy. They're almost free.
That was Terrence.
How does, that's right. That's
Not
right.
this economy.
So I kind of want to do just a warm up. I don't think we did this problem, but I want to find the surface area. So find, did we do a surface area of a cone last time? We didn't do that. I don't know. Okay, yeah, that doesn't sound, just the what?
Cylinder.
Oh, we did a cylinder. Did we have the weird funky, wait, can I see the example?
That's the one we did at the end of class, the XY.
Oh, yeah, that's the one okay, thank you. Thanks, Camille. We don't want to start there then. So we're gonna start with some bigger stuff. All right, I have got in 3D space a giant potato. So this is a solid in space, maybe like a Cheeto or something like that. Kind of looks a little more Cheeto-esque. Blob of crap floating in space. There we go. Don't mean to be too technical, but that's what it is. And we're gonna call this S for solid. And we have a function that can look at each point inside this surface, and we're gonna call that function f of x, y, z. And it returns something. So this could be the temperature at a point. This could be the density at a point. It could be lots of things. It could even be the velocity at a point or something like that. I guess it couldn't be velocity, but speed or something. What other kind of things do scientists measure in solids? I have down here pressure. Does it make sense to talk about pressure at a point?
Yeah.
Can pressure change from point to point?
Yeah, definitely.
Isn't there some kind of ideal gas law where pressure becomes like all constant across
Isn't there?
like?
Well, pressure is force over area, so if your force in that spot's gonna be higher, then you have a higher pressure.
Or if you have a bigger area.
Or if you have a bigger area.
But it
But
could
at that
change.
point-
So you could have like a region in space where there's different pressures at each
Yeah.
point.
Definitely.
Yeah. Okay. Okay. All right. Okay. Cool. Or pressure. Just add that in there. Anything you might want to measure about something that lives in three-dimensional space, that's what F could represent. So let's think about how we might deal with this thing. In particular, let's actually work with the density idea. So let's stick with that because I think it adapts itself to lots of different things. I'm going to have this density function that equals the mass per unit volume. This was a nice example. We can get a lot of mileage out of that. So we want the mass of this entire thing. That's not me, is it? Okay, cool. So I want the mass of S given this density function. So this thing's got different concentrations throughout it. Some spots it's super light and airy, and other spots it's all dense. So we don't quite know what the mass is. And the only way to figure it out is to use calculus. So guess what? We're going to cut it up into nice little pieces, little cubes. And we're going to use each little cube as an approximation of a particular region. We're going to assume things are constant on that cube, get the mass of each cube, add up all the masses, and we're good to go. So, what's our plan? As always, we're going to cut S into smaller cubes. Small cubes. We can say small cubes. Smaller sounds like it was originally a cube. And we do this by partitioning the x-axis, partitioning the y-axis, and now partitioning the z-axis. So we're going to have, I think I can kind of just talk this through. So partition the x range, y range, and z range. Into, oh gosh, let's just be a little bit more precise here, as follows. Yeah, I just need to be precise. So on the x range, I've got, actually, let's do something a little bit different. Oh, Jesus Christ. Oops. Stop the tape.
Thank you.
I think it's okay. I think it's okay. What we're going to do is look for some shadow underneath this thing. So we're going to think of this thing as having a shadow, that when I put the sun straight overhead, I cast it down, and it's actually got some region down here in the plane that makes its shadow. Of this. Does that make sense? Kind of, yeah. So what I'm gonna do is I'm gonna partition that shadow. It might not be a rectangle. This thing might not be a cube, so I wanna do a count for that. Make as follows. So delta x equals the width of the x cuts, delta y, and these are gonna be constant. We're not gonna assume they're different cuts at different spots. We're just cutting evenly for this. Equals the width of the y cuts, and delta z equals the width of the z cuts. So what comes of making these cuts are these little resulting cubes, and the sum of these cube volumes makes up the total volume. So here we have at each point a cube and a rectangular prism, because I don't know that they're all the same, representing a point x sub I star, y sub j star, z sub k star. So I've got this little point deep inside here. This, yeah. So I've got this little point inside here. J star, z sub k star. And that's going to be the representative for this whole thing. And erstwhile, the sides of it are going to look like this. Delta x, delta y, delta z. Is this making sense? Sorry, I'm like, this whole day has been feeling very dissociative, so I'm assuming I'm saying words and I'm actually with you all.
So that's one cube.
Yes.
That's one delta x, delta y, delta z.
Correct, yeah. So that is just one of the resulting cubes from inside
There's like
here.
infinite of those.
Yes, sir. Yeah. Well, there's finite many. Boy, it's starting to look upside down. The way I've got this is kind of weird. So inside here, I've got a bunch of little cubes after cutting this thing up. Some of them aren't going to be perfect cubes, some, like especially when you get near the edge. But the smaller the cubes get,
More precise.
the more precise it will get, and you'll have less
Sure.
I'm not a full cube kind of things going on.
Right.
Does that make sense? So inside here is x sub, that's y sub j, and then I've got x sub I, and then the height of that thing would be z sub j. Star, star, star. And that's the point right in the center. And so I want to find the volume, excuse me, the mass of that cube. So the mass of the ij kth subcube is the volume times the representative density. Because the density might not actually be the same through all that, but we're going to presume it is, and as that cube gets smaller, that becomes truer and truer of the representative representing the whole thing. So times volume representative, rho x sub I star, y sub j star, z sub k star. And what's my volume? It's just delta x, delta y, delta z. So i.e., we've got rho of x I star, y j star, z k star, times delta x, delta y, delta z. We're going to add them all up, and you're going to see a Riemann sum, and the Riemann sum will become a what?
Integral.
Integral. Yes, sir. Question.
I probably should have asked this sooner, but I don't fully understand what the x I star is, like the point inside of the cube.
Yes. So.
I should say, I understand that the coordinates you wrote are representing the point inside of the cube. I don't know what the point is.
I appreciate that. So the point can be any point inside that cube.
Right, I got that. But what is it? Why? Why do we have it?
Well, let's think about how we do it. Like, yeah, let's come back to just good old Calc 1 integration. How did that work? Well, we only had one thing to cut up here, and we cut that up into, you know, n pieces. And then we grabbed a representative out of each one.
Right.
So delta x y star, and that's what I'm going to use. I'm going to use the value of the function at that point
Yep.
to basically kind of represent everybody who's in there.
Oh, so it is representing like everything inside the cube still?
Yes.
Okay.
100%.
Okay, cool.
Thanks for asking. Those are
Yeah,
good
yeah.
questions.
Yeah,
Yeah. Any other questions on the setup? Yes.
And is the star just notate that it's a specific point for I or xi?
Yeah, it's just kind of a classic notation. Just that this is a fixed point inside here.
Okay.
Yes. Any other questions? These are great. So once I get that in, Alexander, you're totally cool on that.
Yeah, that makes sense. It's
Awesome,
like the
awesome.
three-dimensional version of that.
Yeah,
Yeah.
exactly.
Uh-huh.
So let's add up all the volumes. And this is going to be a sum of I equals 1 to m, sum j equals 1 to n, sum k equals 1 to, let's say, L. We don't know how many cuts in each of these axes there are. And then my rho, I'm going to add up all these approximate masses. This right here would be the approximate mass of that weird peanut shape over there, Mr. Potato Head, whatever that thing is. And now I'm going to let all the numbers of cuts go to infinity. Or, so there's two ways to say this, and I just want to point it out every time. I can let m, n, and l go to infinity. Or conversely, I can let delta x, delta y, delta z go to 0. So the width of the cuts going to 0 means infinite cuts. Infinite cuts means width goes to 0. Does that make sense?
Yeah.
Cool, cool. And when I do that, guess what I get? These are going to be my differentials. These are going to become integrals. So let's just put triple there. We're not going to put ranges on them yet. Rho of x, y, z, dx, dy, dz. And more general, and then this would be taken over that entire region S over there. So I'm integrating over the whole thing. The range of x, y, and z values is over the entire thing over there. And another way to write this, we might not be using little boxes. In fact, we're not going to very shortly. So I could say that the mass, let's put this here, the mass equals, or the mass equals integral, triple integral over S, density function, and then put dV here. This is the general volume and element. General volume element. And we saw how that changed with polar coordinates. Well, we had just area. Yeah, we had dA, yeah. And dA could be dx dy, dy dx, or r dr d theta. So we're gonna have those kind of options here. Now, if rho is constantly 1, I just get the volume. So if rho is constantly 1, we get volume is equal to the volume of S equals the triple integral over S dV. And I gotta pee. I'll be right back. I don't know what's up with me today. Like, my bladder is in terrible shape because it's being old.
Oh, is that Barcelona?
Bring this, make sure you know I wash my hands. Always good to know. All right, so let's see, here's my notes. Where are we moving next? We're gonna do some examples. Let's do a problem. Bless you. So let's find a nice, simple volume. So the volume of the solid, S, bounded by, and so this is gonna get fancy. So first off, it's bounded by the first octave, which means X is positive, Y is positive, Z is positive, the one we always draw and look at. First octave and the plane, where's my plane? I won't make us get the plane equation. I feel like we already did a little of that. 3x plus y plus 2z equals 6. Might even be the same plane we had yesterday, or Wednesday, or Monday. It sure feels like it.
Oh, that is.
Isn't it? It's, yeah.
That was the equation.
It was exactly that. That's cool. We'll get to repeat it just a little bit. That's okay, because we got some practice to do. So, what we need to do is describe this thing as a triple integral. And that's going to be part of our fun right here. So the volume equals basically the description of S. Well, let's think about how this is going to work. Let's actually draw the beast first. So first octant, X, Y, Z, when these two are 0, X is 2. When these two are 0, Y is 6. And when these two are 0, Z is 3. Oop, 3. So we got a nice, easy to sketch plane. And we've got this triangular prism that we're finding the area. Can you see it? It's kind of got a side like that. So we're going to find the volume of that solid right there. So here's the hard part of all this. We have to figure out how we're going to cut this thing up. And I guess let's try to go for the low-hanging fruit first. Is there any particular side that I can just make cuts across? This one's pretty chill. I'm going to actually first make cuts that go across like that. So I'm going to cut my biggest cuts along the x-axis, so 0 to 2. So I'm partitioning this x-axis up. And now I need to describe, as I move across here, what are the various y heights. So for example, when I'm here, I've got a very limited palette of y values. Here it's even more limited. When I'm here, I don't really have that many restrictions on y, except that it has to go 0 to 6. But can you see that as the x slice changes, the y maximum changes as well? So for this one, let's see, so dx, that's my outside. Now I'm going to work in. For every x slice, what does the y run? Can you find that? Can you take a minute? So for a particular x slice, let's label it here. I know I'm saying this kind of weird. What is the range of the y values? So y range. We did kind of do this, but it's good to do it again for general x slice. you gotta find that? You got a cup, Czar? Anybody want some tea?
Try it out.
I got an empty water bottle.
Could just fill it up. I could put some in there if you'd like some.
I would like
Just bring a cup today.
Indeed.
You gotta find me a metal mug, like, you know,
You gotta find-
so I can clip it to my.
So you can clip it to your, There you go.
Appreciate
You're welcome. This is a very nice white tea. Very, very gentle. Is this it?
Yeah.
We're in here? Okay. It's not super high in caffeine. I think the temperature's probably nice. Anybody else need? No? Yeah, let it cool a little bit. Don't burn yourself. Burn yourself, then sue me. That's the way to do it.
Alright. Kinda got you.
You all right?
We assume all liability.
What's that?
I think we assume all liability.
Yeah, I assume all. Yeah, definitely. Constantly assuming liability. Can anybody help me figure out how to do this? Yeah. What'd you do?
I took the X, how much the range of that, and the range of Y, and used it that way.
So say more. That's very vague.
It is very big.
Did you do algebra?
A little bit, yeah. I just put 0 to 3x because I divided the y by the x to get like a slope, I guess, of that line on the x y axis. So I just found the slope of that and then set that.
So what did you
as
get?
the range.
What did you get here? Well, the proof will be in the pudding. What did you get for the range here?
I did from 0 to 3x. So
I don't think that's right, but
it's a shot.
it's a, it's a shot. Daniel.
Would you make Z like 0 and then solve for Y?
So let's figure out the equation of this line down here first. So set z equal to 0. So here, when z equals 0, what are we going to get? We're going to get 3x. You're kind of close, Daniel, but there's a little bit more to it. So this tells me that y equals 6 minus 3x. So for every x coordinate, that tells me the max y that I can go to. So when x is 0, the max y is 6. When x is 2, the max y is 0. You can't move at all. And then this gets all the guys in between. So you had the right idea, Daniel. You just came up with not exactly the right equation, but you got the free slope and everything in there, so, you know, 6 minus 3x. So this sets the x coordinate. This uses the set x coordinate. And now at this point, we have x, y determined. So by the time you move to this inner integral, see, these guys are setting the x and y coordinates for this one to use. And so once we get to this inner integral, we've actually got our spot down here that we're going to use. And now we have to figure out what is the range on the z values for a particular x, y. How high can I go? And we're definitely starting at 0 on the z-axis. We're starting at ground level. How high do we go? How do we find it? What are you saying, Kayla?
Set x equal to 0 and find the equation. The
X.
y.
Well, we don't necessarily want to set x equal to 0 because x might not be 0. But this,
Do we just, sorry.
it's okay.
No, he's just gonna say this.
Go for it.
Gonna say
Do we just solve for Z?
Solve this for z. So we need to figure out what is the z coordinate on this upper shell, on this roof, given an x and y coordinate. So we're going to solve this thing for z. And that means once I'm at x, y, the max height I would have here is given by this formula. So it's going to be 3 minus 3 halves x minus 1 half y. And since we're doing volume, our density is 1. And then this was dz, dy, and dx. Does that make sense?
is it we wanna do?
Because we're just doing the volume, and we're assuming the density is constantly 1. I didn't get a density function, and anytime you're doing volume, just this formula here. Does that make sense?
Any other questions on that? 'Cause I wanna see what kind of time we got here.
Heck, hey, could you do it like this really quick for me? Maybe, I think you can do it quick. Set it up now, but do dx, dz, dy. That'll be a good exercise. If you can do that, you got it. So start on the outside. What are your y slices going to range? You know, start with the low-hanging fruit, work your way inward. Just a reminder, we don't meet on Friday, but I will record something for you. And it might just be working some problems to give you examples to look at. I don't know, anybody else got what I got? Got that? Yeah, just take a minute, make sure you get somewhere, and let's talk about it if that isn't making sense.
Let's talk about it.
Let's talk about it? Okay, cool. So first off, low-hanging fruit, what's the y range? 0 to 6. That makes sense? Got that one? Okay, cool. So let's pull this little bottom rectangle out. And actually here, I kind of need to look ahead just a little bit, Czar. I noticed that these outer two are z and y. So what that means is that the inside integral, the one that says dx on it, is going to use information from y and z coordinates that I feed in from the outer two. Does that make sense? So you gotta think about integral on the outside feeds inner integral. So y goes from 0 to 6. When I'm at a particular y location, what is the z range then? So instantly I've got a restriction on how z can go. It's going to start at z equals 0 down on the bottom, up to here. Well, when I'm in that plane, I've got x equals 0, because I'm in the yz plane. So when x is 0, here's what the equation looks like, right? Kind of just set that to 0. So I see that y plus 2z is 6, and that means that z is 3 minus half y if I solve for it. So when I'm here at a particular y spot, the y runs from z equals 0 to z equals 3 minus 1 half y. That's this top spot here. Does that make sense? You sure? Okay. So that's where the 3 minus 1 half y came from. Now I've got these two totally determining the z and the y coordinate. And so I have to ask myself in here, if I know the y and the z, what does the x do? So once I've got y and z, I'm in this little plane over here, and I'm extending out in the x direction. So then I come here and I go, okay, well, if I know x, y, and z, well, where the hell is it? If I know y and z, what's x in terms of y and z? And so I just took the original equation, solved for x in terms of y and z. And so that's how I got that upper limit there.
Does that make, to me, it's just making sense of where we are on the
Yeah, it takes some practice, mental exercise. Is this making sense? Okay, let's try some fancier ones now. Let's actually introduce two new coordinate systems all at once. What the heck? Why not? So, two new coordinate systems. Good news is the first one you already know. It's polar coordinates with a z added on. So you do polar stuff and then you can raise it up or down by the z height. So the two new coordinate systems. First one, cylindrical coordinates. So we have to be able to navigate to anywhere in the plane, in space. So the first thing we do is use polar coordinates in the xy plane to get to where you want. So if I'm right here in the xy plane, well, let's say I'm like right here. So rectangular coordinate wise, it would look like this. But with polar coordinates, I'm going to draw a line out to here, that's going to be r. So how far I have to go to be underneath that point, that's r. And then I'm going to sweep theta radians away from the positive x-axis. This is confusing when you see it here, because what you're used to seeing is theta being swept like this, but that's the positive x moving toward the positive y. Here, positive x moving toward positive y. And then once you get swept right underneath the point you want, you raise up by that amount. And so the coordinates will be r, theta, and then how high up or how far down you have to drop. Pretty chill. Pretty chill. So that's cylindrical. And cylindrical coordinates look like this. And we'll assume that, r is between 0 and infinity, and theta can be pretty much whatever you want. 0 to 2 pi gets you a full revolution, but this is probably the only restriction we really want to put on there. We don't really need negative z's. This gets rid of some ambiguity, so you don't have negative radii. You don't need them. You spin around the other direction if you need it. So this one's not too big a stretch. The next one is much more of a stretch. The next one is, and here, our volume element, dv, is r dr d theta. This is your polar planar element, and then tack on a dz. So remember, this is just from the polar stuff. We kind of went through a derivation of that. That's the polar part. Now, I'm not going to derive this next one. You can read about it, but it would take the whole class to actually derive these spherical things. I don't think it's worth our time, but we can talk about how they work. And they're kind of cool. So you start off in the polar situation, but then how you get the height on it is what changes here. So let's see, let's go to the same point right here. And I want to locate that. So the first thing I do is I locate underneath it using polar coordinates. And so this is going to be r. This is going to be theta. So it's just like this way I started out over here, except instead of saying how high up I'm going to go, now I'm going to think about a line that starts up straight up the z-axis, and sweeps through this plane that I've kind of cut here, right? This is an angular plane. If you just extend this r all the way out, we're going to drop an angle from straight up to over to here, and we're going to call that phi. So we drop from straight up. We need to practice this guy a little bit here. So that's theta, that distance is r, and all together, oh, actually, no, sorry, we don't use this r. We use this r right here. That's just how far we go. So we sweep over, sorry about that. We sweep over to here, we sweep down, and then rho is how far out we head along that axis. So it's a little bit more than that. So we have rho, theta, phi are our coordinates. Let's actually practice, because I kind of screwed up the opening on that. So write each point in cylindrical and spherical coordinates. And we'll do some of these together. So let's say I've got oh, how about this? 1, 1, 1. So let's convert this. And let's actually get the formulas up here too, which will help with all of this. This one we can kind of figure out just by drawing it. So 1, 1, 1 is 1 out on x. So this is in rectangular. 1 out on y, 1 out on z. So you're kind of just at the tip of this cube right here. A 1 by 1 by 1 cube. And we're at the tip of it. So. Pretty bad. Okay, I guess that kind of makes it. So let's think about how we're going to do this. How far do I have to rotate over to get in line with that point? Pi over 4. That's a 45-degree angle. So here we've got theta equals pi over 4. How far down? Ooh, gosh, is that? Now I'm starting to wonder if that's 45 degrees as well.
Should be, shouldn't.
It seems like it should be. Let's take a look from the side. You know what I'm saying?
I do see what you mean, yeah.
Let's see, because that cube, oh, so that cube, what's the diagonal here? Square root of 2? And then the height is 1. So I'm looking at this thing from an angle. So here's the z-axis, but I'm looking from the side. Here's the crease on the side. That's actually square root of 2 right there, and a height of 1. So this would be my phi here. So what is that? It's not 45 degrees, it's actually a little different.
But it would be more, yeah.
It would be more. Yeah. Okay, that wasn't as easy as I was hoping it would be. Let's get the conversion formulas up here and then use those to make life a little bit easier. So, formulas. To convert rectangular XYZ to cylindrical. So let's do cylindrical here. This one's pretty easy. Your x, let's see, wait, so your r is just going to be square root of x squared plus y squared. It's just living in the plane down there. It doesn't even know about z. And your theta is the arctan y over x. And your z is just your z coordinate. So you just kind of copy that down. But for spherical, it's a lot fancier. So here, the rho is square root of x squared plus y squared plus z squared. It's the distance from this point to the origin. So it's just the modulus of that point, or the magnitude. Tangent of phi is again y over x, so same thing as I just said here. In the tangent form, as opposed to the arctan form. But then the cosine of phi equals z over rho. So let's go ahead and crank this out now that we got our formulas. So for us, let's do the spherical first. Spherical. And here I'm using x equals y equals z equals 1. So rho is going to be square root of 3, using this formula. Tangent of theta is going to be 1 over 1. So that is theta is pi over 4. And then here's the one that was looking a little brutal, and I'm glad we stopped. Cosine of phi is 1 over rho. Anybody got a calculator you can help me with? Can somebody do an arc cos of 1 over root 3 for me? Because I...
Root 3?
Yes.
Oh, okay.
Yeah, because, so what it was, Talon, I can explain how, from the side here, when we look at this cube from the side, you've got that long diagonal from the origin to the
Oh,
tip,
yeah,
and
yeah.
that's root 3.
Okay.
Does that make sense? Yeah, yeah. So your hypotenuse ends up being 3, root 3. What do we get, like 37 degrees? Yeah, somebody give me degrees just so I get a feel for it.
It's about 55,
55 degrees.
rounded up.
Okay, yeah, 55 degrees. And then what was it in red? Just,
0.95.
that's good enough. Cool. So the coordinates look pretty terrible. So 1, 1, 1 rectangular is equivalent to square root of 3 pi over 4 comma 0.95 in spherical. Let's do the polar really quick while we're here, or the cylindrical coordinates. Cylindrical's way easier. So what are we gonna get? So in cylindrical, r is just square root of 2. Theta is the same thing. And then z is sweet old 1. I'm sure that's all making sense. If not, let's talk. Yes, ma'am.
Two questions.
Yes.
Arc theta is arctan of y over x? Or
Yes, that is
okay.
y over x, yes.
And then for a spherical, we don't have any bounds for any of those?
Yeah, so that's a good question. I guess generally we would probably make sure that rho was greater than or equal to 0. And I think, oh yeah, and that's a great question, Camila. And then phi would be between 0 and pi over 2. So we don't allow the phi to keep wrapping around, it just points the height. Yeah, good question. Very good question. Let's put up a couple other formulas here too. Oh, let's actually look at why you might even want to see something in polar or spherical. What's the equation of a sphere of radius 2 in spherical coordinates? Sphere of radius 2 in spherical. What's the equation? Think. We want to be able to point in any direction. What do we want fixed?
Follow.
Yeah, our rho.
Row, that's what it is.
If I just set rho equal to 2, that's the equation of that sphere. So certain things become very beautiful because this is saying, go to the plane, go to the space, look at all the points that are exactly 2 units away from the center. Yes, sir.
For negative z axis, do you put phi as still 0 to 2 pi? For anything that goes below?
So yes, so, well, wait, ask your question again, sorry.
For any 3D object that goes below the z-axis,
Yeah.
to negative z, is it still 0 to 2 pi for phi?
No, the phi is just gonna go 0 to pi over 2, so if it's just a side view, this would be phi is between 0 and, did I say 0 pi over 2? I meant pi, sorry.
Oh, okay.
That's probably why you were confused. Yeah, sorry, that should be pi, because we want a full 180 here. Pi less than pi over 2, phi less than pi over 2 keeps you in the first quadrant. Does that feel better?
Yes.
Thank you, yeah, thank you for asking that. Let's see. Yeah, okay. So let's get a couple formulas out here that we can use to make life a little less required. You're still gonna have to do some thinking, but it's nice to have formulas as well. So I gave you the spherical, or the cylindrical volume elements. So let's put those up here again. Volume elements. So rectangular is some perturbation of those 3. You can do those in any order. Cylindrical, I gave you, that was r dr d theta d phi, or dz. And then spherical, the volume element, this is pretty weird. So in spherical, the volume element is rho squared sine of phi. And then these 3 can go in any order you want. But you have to put this in. This is kind of like the r that we toss in cylindrical, but now you've got to add that guy into your integral. So how would you even use that? If I gave you some integral and I said, find this integral, and you wanted to do it in spherical, because this S is a sphere, or some part of a sphere, that would be the reason you'd want to do this. Then you convert it the following way. So it's going to be triple integral over S. You're going to have to describe S using these elements here as opposed to whatever was here. We're going to take F and we're going to replace the X with R cosine of theta sine of phi. So this is your X replacement. This is just the backward version of the coordinate transformations. Then rho sine of theta sine of phi. That's your Y. And then finally rho cosine of phi. And then out here, your volume element is going to be rho squared sine of phi d rho d phi d theta, however you want that. D phi. So this is spherical. If I wanted to do this in rectangular, or excuse me, cylindrical, let's just put the whole formula up here. So this is cylindrical. we're gonna have triple integral over your surface described in cylindrical coordinates. F of the x is r cosine of theta. The y is r sine of theta. And the z is just z again. And we'll put these to use after I get these all up here. R dr d theta dz. And now we got enough that we should be able to do some stuff. Oh, I'll put it myself. Cheers. Okay. Make sure to watch the recording. Thank you. So let's do some examples of this. Okay, I've got a few set up here. Hope I got a few set up here. Oh yeah, okay. So let's convert this one to cylindrical coordinates. So I'm going to give us an integral and we're going to rewrite it using this second form here. So the first integral, and it will give you integral 0 to 1, integral minus square root of 1 minus x squared to positive square root of 1 minus x squared. The inner integral goes from negative quantity x squared plus y squared, and the upper limit is positive x squared plus y squared. 21xy squared dz dy dx. Holy shit, we got some work to do. So anytime you're asked to convert an integral into new coordinates, first thing is you need to understand what you're integrating over. And that could be the hardest part of it all. So step one is, what is the region we're integrating over here? So what is the solid of integration? What does it look like? So the first thing is we can work outward or inward. But remember how these guys right out here, this is totally describing where my y and x came from. So these two integrals out here describe the region in the xy plane that we're integrating over. Let's actually just take a look at xy while we're here. So the x runs from 0 to 1. I've got that. Meanwhile, the y, and you might want to write this out until you're used to seeing these things. The y runs from negative root 1 minus x squared to y equals positive 1 minus x squared. What the hell is that? Circle. Do we see the circle going on? It's the top half and bottom half of a circle. We've been seeing a lot of circles this semester. This is like the one thing I hope you can recognize a little bit. So notice here that y squared equals 1 minus x squared. That's x squared plus y squared is 1. Same thing here. They both get you to that. They're just top and bottom of the circle. So this thing here, this is my x range. This is a circle of radius 1. This is the bottom half of a circle of radius 1. And so that means my entire first region looks like this, and I'm integrating along these strips. So for a particular x value, I go from negative 1 minus x squared rooted to positive 1 minus x squared rooted. Yeah? All right. So that's the region in the xy plane that we're integrating over. We can get this a little fancier now. So let's see, here's x, y, z. So it looks like we might need, let's see, so it's just positive x-axis, and there's 1, there's 1, there's 1. Now you get to have some fun trying to draw perspective. There's our base. What are we integrating for height? We're going from, so on height now, at each of the x, y points that we've determined in this region from the outer two integrals, we go from z equals negative x squared plus y squared to z equals positive x squared plus y squared. So on the inside, once we have the xy coordinate, we see z runs from z equals negative x squared plus y squared to z equals positive. What the heck is that? Any ideas on what that shape looks like? What does this look like? And now we're going back to like week 1 of the class, week 2 of the class. What? Sphere. Close. Not a sphere. If this was, it doesn't have enough squares to be a sphere, but it's close. It's related to that.
Cylinder?
Not a cylinder, but it is. It does go
Oh,
out.
it's the.
What are your slices?
That's what you take the front half of the sphere.
Yeah. So no. What is that shape, right? What's z equals x squared look like? Parabola. What's z equals y squared look like? A parabola.
Paraboloid.
So it's a paraboloid, yes. So check it out. We can do this. We just got to settle down and then realize we got this. When x is 0, you got z equals y squared. When y equals 0, you got z equals x squared. Now, what do the level surfaces look like for different z's? Circles. Now those are the circles. Yeah. When z is 1, it's a circle of radius 1. When z is 4, it's a circle of radius 2. So it's a paraboloid. This is a paraboloid like that, and this is its negative. So what we actually have is on top, we've got good old z equals x squared plus y squared, and then underneath it, kind of like a companion, like this, z equals negative x squared plus y squared. And that sits here somehow. I've got it, boy, this is going to be fun to draw. But right here, I've got my surface like this. So that's actually going to be, that's the top of my thing. And then this comes down like this. And then there's one underneath as well. Something like that. That's not great. That's a little better there. But it's this shape that I'm finding the area of. So the thing I'm finding the area of is kind of like an hourglass. And it's half of this too, right? It's not even the whole thing. So it's this weird shape between these two bumps. I don't even quite know how to explain what that looks like with like, anybody got good words for that?
If you cut an hourglass in half.
It's like half an hourglass, yeah. And it's the space between the two lobes of the hourglass that we're actually finding.
Oh,
Is that it, right?
that makes more sense.
Yeah.
I thought
Yeah, we're finding the volume of the stuff outside the hourglass.
Okay.
Odd. Quite odd. Yes, not quite time yet. Almost, Helen. Almost. All right, we got to do, oh, we're not even done yet because that's just the limits on the outside. So let's come over here. We still got work to do because I have to convert this all into polar form now, or cylindrical form. How am I going to describe this part in cylindrical coordinates? So let's come over to cylindrical now. How do I describe this first region, this guy here, this guy here? How do we do that in polar? What's your theta range? Well, I hear lots of pi's and zeros.
Pi over 2 to pi
Pi.
over 2.
Negative pi over 2 to positive pi over 2?
Yeah, and
That
then
would
R
work.
would be 0 to 1.
And then 0 to 1 on the radius.
Yeah.
So you see that? We're gonna sweep from minus 90 to positive 90. And then the radius has to be everything between 0 and 1. So out here, I'm gonna put R on the outside. That's okay. Doesn't matter what order these guys are in. I'll definitely put my R in there. My extra R has to be in there the minute I go over. Theta is going to run from negative pi halves to pi halves. And Z now, Z is going to run from here to here, but I don't have any X, Y's anymore. What are these two guys in terms of polar coordinates? R squared?
Yeah.
Indeed. So from minus R squared to R squared. And now I'm almost done, but not quite, because there's a freaking integrand. So we have to go use the conversion formulas, which if I didn't put them all up, they're definitely in the book or available online, but I think I put these up here. X is our cosine theta, Y is our sine theta, and Z is just Z, so that's all good. So you're gonna plug those in directly for the X, Y, and Z. So this becomes 21 times the X, which is our cosine theta. That's your X. And that R came along for the ride because we switched over to a polary kind of thing. And then this is going to be the Y, which is our sine theta. And that's all squared. And you could probably leave it like that. We're definitely not going to do it. We're definitely not doing it. I'm going to rewrite it one more time. So it's integral 0 to 1, integral negative pi halves to pi halves, integral negative R squared to R squared. And then pull the 21 out in front. And this becomes R to the 4th, okay, right? Because there's an R squared, there's 2 more R's. Cos theta, sine squared theta, d theta, dr, dz. Yes, ma'am. Did I do something wrong?
I'm just making sure, is like the inside integral dz?
Did I have, yes, that's right, I forgot to put the dz. The good news is, yes, you're right, ma'am, thank you. Yep, that can't be changed. So that was, thanks, Kayla. That was dz, and I think, Christian, you were gonna say something about that too. And let me get everybody synced up. Yes, thank you. One minute. Oh shit, I'll just make some lecture stuff up so you can see it. Alexander's about dead anyway. That's not dying over there. So I'll do some examples and put up a video for you. Things that will help you on those skills checks. That'll be my goal. And I'll have that done tomorrow. Christian, when you get a chance, would you hit? Thank you, sir.